Hello everyone and welcome back to my channel. So I've made some improvements to the basic Vien bridge oscillator that I presented in previous videos. Namely, it exhibits very low distortion now, and also I can even adjust the output amplitude through a potentiometer rather than having it fixed. One change I made is I've eliminated the diodes in the feedback loop and replaced it with a automatic gain control circuit, which I'll show you momentarily. But needless to say, it performs very well. The distortion is very low. It's almost a perfect sine output. Let's just go to the FFT graph and have a look. The oscillator frequency output at number 1 there, which is 1.35 dBV, and I guess the first harmonic would be double that, would be about right there, and that is about sometimes it just flashes up on the screen here, 40, it's almost 40 dB, 30 dB below the output, 35 at least below the fundamental output frequency. So we'll look at the sine wave output again. Well, it looks very much like almost a perfect sine wave. Well, let's bring up the output from the signal frequency generator and compare the shapes of the sine waves. Okay, so I have on display here the purple trace, which is output from the signal frequency generator. So that's the bottom purple sine wave. Set about the same amplitude as output from the new improved version of the Vien bridge oscillator. They look very much like sine waves, very much. So let's have a look at the Fourier spectrum for comparison. Fourier spectrum of the Siglent function generator. Okay, so I have the output from the improved Vien bridge oscillator on screen, the Fourier spectrum. So I've changed the scales to 10 dB per vertical division. So fundamental tone output is at plus 14 dB. First harmonic, doubling of the frequency, is about at minus 35. So there's like a 49 dB difference between the first distortion product. Well, sometimes it flashes up on the screen, but it's not the right one. 49 dB, 50 dB difference between the fundamental and the first harmonic distortion product. So let's switch over to the Siglent function generator for comparison. This is a DC component being shown here because the oscillator is actually DC coupled at the moment with the oscilloscope. Okay, so about the same amplitude level, and Siglent is not producing much in the first harmonic, but it's producing something in the third harmonic, which is much less than this jitter that we see in the what would correspond to the first harmonic. But first harmonic on the Vien bridge was about there. This one is about here. So it is a little bit better, but by about 10 dB or something like that. But I think it's not that significant. I also have another adjustment on the Vien bridge oscillator that supposedly it is a distortion adjustment according to the literature that I've read, but let's see. Oh, oh, look at that. If I do adjust it, I can make the first harmonic actually go down. Now it's as good as the siglent right there. So the literature was correct. It is a distortion adjustment. I'll get into the circuit a little bit, but let's just see how it all works out at first. So now I have my Vien bridge oscillator, the improved version, just as good as far as performance on the distortion products go as my siglent. So let's switch over to the siglent and have a look. Well, is there a difference? Yeah, well, not much now. So that works out fairly well. Let's have a look at the circuit. What on earth am I rambling about that is so exciting? Well, let's just recap what we had done previously as far as the Vien bridge oscillator. So we had to control the output swing, we had these two diodes in the feedback loop that pretty much limited the output excursions to about 3 volts peak to peak. And these are the capacitor, resistor, digital potentiometers that were used to adjust the frequency in the previous video. And so what have we done now that is different? Okay, let's have a look. Okay, I should have it on the screen now. Okay, so here's the basic Vien bridge oscillator with the resistors and capacitors in the feedback loop, positive feedback loop. Here's the negative feedback loop. And what else do we have in here now? We have a JFET, which it basically acts like a voltage controlled resistor. And the control voltage comes from this integrator comparator, which is taking part of the output signal, positive going voltage swings, going through this low voltage turn on germanium diode, and going into a summing point at pin 6, and it's being summed with a reference voltage, which is adjustable in between ground and this 1/2 V plus, which I call virtual ground. That is basically just the output from a voltage divider or transistor amplifier. That looks like that. So this is the voltage divider at the base, add a 1N914 diode for the VBE voltage drop, and the 1/2, this is V plus, the 1/2 V plus comes out of the emitter point from this transistor. So it's like a kind of a regulated power supply. That's how it works. Okay, so since I'm using single rail supplies, I have a V plus, I have a ground, and I need to have also a virtual ground because the or a halfway point between V plus and ground, because the original circuit was done with split power supplies. So I have this integrator, or basically a fancy low pass filter in the feedback loop, a second feedback loop, which forms a automatic gain control circuit along with the JFET. So what's happening is, as the output voltage swings higher, it'll sum more positive. It'll sum more positive voltage to pin 6, which will in turn make pin 7, with respect to 1/2 V plus, drop, go negative, which will in turn increase the resistance between drain to source of the JFET. So since the JFET is in the negative feedback branch of the oscillator, what's happening is it reduces the gain as the output increases, and it'll increase the gain if the output drops. So the net effect is to stabilize it to a fixed value of output. And this is the amplitude adjustment that I was playing with before, just changing the reference voltage that that you feed into this voltage divider. And the distortion adjustment is right here. This is actually a potentiometer I have. It's not fixed resistor. And what's happening is, to produce the best results, you need to match up the total resistance, drain to source, with this plus this 4.7K plus 220 ohm resistor. Make it basically the ratio of this resistance to the resistance of the drain to source plus this 4.7K and 220 ohm resistor should be 3. So the closer you get it to 3, with the 4.7K and the sum total of these two, the less contribution the JFET will need to make. So the JFET is a little bit on the nonlinear side. It's a nonlinear device as far as source to drain resistance. So that's where the distortion in the output will originate. It'll come from the nonlinear or voltage dependent drain to source resistance of the JFET. So I can show you the JFET curves, and we're attempting to use this JFET in the lowest possible drain to source voltage region as possible to get the most linear effect out of it. And that's kind of how this works. So where does this come from? Well, it comes from a book from 1980 called the Ic Op Amp Cookbook by Walter G. Jung. And his circuit's a little bit different, but as far as some resistor values, but this is what's on the page here is what I found that works. Walter has passed away since I don't know when, and he's no longer around. So another thing I found is the best thing to do is to eliminate this 100K ohm resistor in this feedback branch of the JFET. And I find if you leave it in there, you get some secondary oscillations arising from the AGC loop oscillating, which I will demonstrate just in a minute. But in any case, the best thing to do is to omit it, and the circuit is very stable without it. So this is the circuit on the breadboard, this portion. This is something else. Let's just zoom in on that. So the two potentiometers, distortion reduction adjustment pot is there, amplitude adjustment pot is there, and the rest are, there's the voltage reference 1/2 V plus, JFET is buried in there, the TLV 2772 is in there too. Nothing dramatic about that. So let's have a look and see how the output changes if I add that extra 100K resistor between the drain and the gate of the JFET. Okay, we're back to watching the oscilloscope. So let's see what happens when I add that resistor between the drain and the gate. Oh, look at that. The output jumped. Okay, that's one effect it has. Unexpected gain increase. Let's see if I can reduce it. Not really. I'm adjusting the amplitude adjustment pot, but no, can't do it. Now the distortion pot should also have some degree of, yes, amplitude adjustment, although the amplitude output disappears altogether. So this is operating at 5 volts, so it doesn't give me a heck of a lot of adjustment anyways, but you can always go to a TL072 op amp and increase the voltage, power supply voltage, and see what effect adding that 100K resistor does. Okay, I have that 100K resistor in between the drain and the gate using a TL072 operated at 9 volts. I can get the output to do this. So just to show you what's going on here, if I slow down the scope, well, there you have it. Not only is the Vien bridge oscillator op amp oscillating, but so is the gain control loop. And let's just go to a single trigger, and that's what it looks like. Move it down. Oops, wrong one. Just adjust all of these. That's okay. So the blue trace is the 1/2 V plus level from my virtual ground generator, so it oscillates about that point. But yeah, this is what you get if I include that drain to gate, sorry, resistor, an oscillation of the gain control loop itself. Not something that's desirable. So I find the if you bring anything close to the gate of the JFET, even a scope probe with a long wire lead on it, you can also induce this oscillation. So just to complete this discussion on this AGC loop oscillation, the yellow is the output pin 1 of the oscillator, and the blue is the 1/2 V plus virtual ground, and this purple is pin 7 of the second TL072, or if you want to use the 5-volt version, the TLV2772. It is the gate drive. Eventually, it is the gate drive of the JFET. And as you can see, it's trying to chase and stabilize the output amplitude, but apparently it can't with this extra resistor in place. So here's an example of feedback instability in a nonlinear fashion that occurs in the AGC loop. Feedback, oscillations, and more oscillators. So I have here the data sheet for the J113 JFET that I was using in the AGC loop of this latest and greatest oscillator. So let's have a look at the key performance curves that are of interest to us here. So scrolling on down. Okay. The drain current and drain source voltage and gate to source voltage curves are the ones that are of interest here. So in the loop of that oscillator op amp, the JFET is being used in a very low drain to source voltage region, in this region here. And here these characteristic curves, drain current versus drain to source voltage, are almost straight lines. In fact, the smaller the drain to source voltage, the more tangent and more straighter these lines appear to be. So the resistance, the drain to source resistance, is the inverse of this slope. So it's delta V over delta ID. So as the gate to source voltage decreases, becomes more negative with respect to the source pin, the resistance of the JFET channel increases. And if you're getting out to here, you're operating nonlinear. But for the most part, in that circuit that I showed you, yeah, I even measured it. But although it's not exactly documented on video, the drain to source voltage is pretty low. It's in here. It's in this region. So this is how that the JFET is used as a voltage controlled resistor to control the in a feedback loop, to control the gain and stabilize the gain output of the oscillator.